Hello everyone, and thank you for tuning in. My name is Joseph Ryoo, and I am an assistant professor of marketing at Arizona State University. I am thankful to AMA AI SIG for giving me this opportunity to talk to you about topic models, a tool that I use very frequently, and a tool that has had a wide impact on marketing research, particularly with regards to text analysis. In this video, I'll be going over the following. First, I'll briefly introduce topic models, talking about its motivation, its benefits for us as marketing researchers. I'll also talk about the intuition behind the most popular topic modeling algorithm, latent dirichlet allocation, or LDA. Then talk about its potential applications to marketing research, giving specific examples. And finally, I'll be going over a published study that applies topic model to address its empirical research questions. So let us consider this example. We are marketing researchers and we are handling data that involves text. Maybe we have data from Instagram or Twitter or X now it's called because we're studying online word of mouth amongst consumers. Maybe we're studying customer reviews and so we have data from Amazon.com. Now, before we move any further, I would like to define some terminology that's going to be reoccurring throughout this video. When I refer to a document, what I am referring to is a unit that denotes a collection of words. For example, a particular review is a document. A particular social media post is a document. When I use the term a corpus, what I refer to is the complete set of documents, maybe the complete set of customer reviews that you have collected from Amazon.com. And so the question for us to consider is, do we have to read all the documents in the corpus for us to extract insights? Now, given the particular corpus that we're interested in studying, right from the get-go, we have two potential approaches. First, we can try and manually read each document in the corpus. Second, maybe we can try and count word frequencies, examining which words are the most reoccurring in the corpus. Now, each of these approaches have their strengths, but each of these approaches definitely have their weaknesses. So let us examine both of these approaches in greater detail. Suppose that you opted to manually read the documents in your corpus. The first potential source of weakness with this approach is objectivity. Specifically, we as researchers might have specific incentives that influence how we interpret the text in our data. For example, we might have research questions, we might have hypotheses, we might even have anticipated results in our minds that either consciously or subconsciously influence our interpretations of the data. The second source of weakness is consistency. Suppose you're working in a team of other researchers. Is your interpretation of a particular text going to align with the interpretations of other researchers? The third source of weakness with this approach is intuitively efficiency. As your data size increases, to deal with hundreds of thousands, even millions of documents, the cost in terms of both money and time in analyzing these documents increase substantially. So given the weaknesses that we have just discussed, maybe we're going to opt for the second approach, measuring word frequencies. This is often the very first step of natural language processing. And we're going to be taking our corpus and constructing a document term matrix that looks something like this. A one big matrix where the rows identify the unique documents in our corpus and the columns identify the unique words that appear throughout the documents. Examining the example here, we find that word 5 is the most frequently occurring word in our corpus. So it appears 12 times in our corpus of 3 documents. And examining the rows, we find that document 2 is the document that contains the most words, 16 words. From this matrix, we can extract insights more efficiently compared to the first approach of manually reading the text of these documents. Measuring word frequencies also have its own weaknesses despite the efficiency compared to manually reading documents. The first source of weakness deals with selecting keywords. In our previous example, we have considered a document term matrix with 3 documents with 6 unique words. But as we handle real-life data sets, and as we handle data sets that are much larger in size, we'll be encountering data with a greater number of documents and a greater number of unique words. Since we cannot allocate our research efforts equally across the words that we encounter, we would have to select a subset of words that we focus on for our research. But this decision might encounter similar issues regarding subjectivity as with manually reading the documents. Furthermore, measuring word frequencies also encounter issues regarding word associations. Even though we're able to identify which words occur most frequently, perhaps some words occur frequently together. Perhaps words are correlated. And this relationship might convey ideas, might convey insights for us researchers, but it is very difficult to decipher from document term matrices alone. The third source of weakness is related to this idea. Even though we're able to identify the most frequently occurring words, we're unable to identify the set of words that convey more complex ideas, higher order ideas, or topics, if you will. After discussing the potential drawbacks related to the prior 2 approaches of manually reading the documents in the corpus and counting word frequencies, we finally arrive at topic modeling. And in this domain, we need to consider the seminal paper by Blay, Ng, and Jordan titled Latent Dirichlet Allocation in the journal Machine Learning Research. Latent Dirichlet Allocation, or LDA, was developed primarily for information classification and retrieval. Consider the example of trying to build an online catalog for a library. We have a set of books, and without having to read these books individually, we want to classify these books into categories based on their topics. So we're trying to move beyond individual words to higher order ideas or topics as our unit of analysis. LDA addresses 2 questions. First, how many topics adequately summarize our corpus and which words are representative of each topic? And second, given a particular document, what is the mixture of these topics so that we as researchers are able to decide which topics are important and which topics are less important given the particular document? To illustrate this using an example, consider a corpus of 2 books. Without having to manually read these 2 books individually, what LDA allows us to do is to extract the set of topics that summarizes these 2 books succinctly. So in this example, maybe we extract 3 topics, and these topics may be romance, fantasy, and mystery. So what exactly are the topics that LDA has just extracted from our example corpus of 2 books? The 3 topics that we have discussed of romance, fantasy, and mystery are each distributions of words that are found across the 2 books. The topic of romance might contain the words of love, affection, and like. The topic of fantasy might contain the words of magic, lore, and dream. And the topic of mystery might contain words of death, kill, and surprise. If any of the 2 books contain more of a specific set of words, the book is more likely to contain a particular topic. To review, we have applied LDA to our corpus of 2 books. And by doing so, we have extracted 3 topics, the topics being romance, fantasy, and mystery. And what LDA allows us to do is to summarize the content of our corpus, so the 2 books here, based on these 3 topics alone. And these topics are based on the words that are found in the books. The first book might contain a mixture of topics that look something like this, where the topic of romance is weighed more heavily, here 75%, compared to the other 2 topics. Whereas the second book, based on the words that are found in its content, might contain more of the topic of mystery, 90% compared to romance and fantasy, each being at 5%. We have moved beyond words as our unit of analysis to topics. And this enables us researchers to extract insights that are at a higher level. Enables us to measure associations between words that convey more complex ideas. Being curious, we might wonder, how does LDA actually work? Again, without having to read the books or the documents in our corpus, LDA enables us to identify the set of topics that are shared across the books. And LDA allows us to measure how much each topic is found in a particular book. We can perhaps do this manually, but again, we encounter the issues of subjectivity. How does LDA accomplish this in a statistical or a data-driven manner? Well, LDA is a generative model that attempts to reverse engineer how books were written. LDA attempts to guess which words belong to which topic. And LDA uses data to iteratively refine its guesses, so that in each iteration, the guesses of which words belong to which topics become better and better. We can formally discuss the generative process of LDA, or the process of how does LDA reverse engineer how each document was written, in the following manner. For each document D in our corpus, we first draw a topic distribution, theta D, from a Dirichlet distribution. And this theta D represents the mixture or the weighting of the topics that are found in document D. Once we draw this theta, we move on to the second step. For each W or word that is found in document D, we draw a topic assignment, Z, for that particular word, where N indexes that word found in that document, from a multinomial distribution defined by theta D. After we draw the topic assignment, we then draw a particular word from a separate multinomial distribution defined by phi. The generative process of LDA is based on distributions and probabilities. And the generative process of LDA also is based on the bag of words assumption, which implies that the order of words found in documents do not matter. Let us try and understand the generative process of LDA in relation to our working example of classifying books for a library. LDA tries to reverse engineer how each book was written. Well, suppose you're an author of a specific book in the corpus. LDA tries to take the position of the author in understanding how that book was written in the first place. So, suppose you're writing a book. You have to first decide how much each topic to write about, and that is theta, the mixture or the weighting of the topics found in that particular book. Once theta is drawn, or once you decide how much each topic to write about, we move on to the second step. To write a specific word for that book, you have to first decide which topic to write about. And this is the topic assignment, this is Z. You need to draw which topic to write about from theta before we can then select a particular word to write. And so we move on to the third step. After we draw a specific topic from theta, we can then select which word to write about based on the distribution of words belonging to that particular topic. Let us go back to the example of our corpus with 2 books. We have applied LDA and extracted 3 topics: romance, fantasy, and mystery. LDA tries to reverse engineer how this particular book was written in the first place. If I was an author of this book, containing perhaps 1,000 words, for each word I write, I have to first draw a particular topic assignment that is based on theta. Maybe this book, the theta suggests that romance is weighted 75%, fantasy 20%, mystery 5%. If I'm writing a particular word, suppose I drew the topic of romance because it's weighed more heavily. I then draw a particular word related to that topic of romance. And that word might be love, might be affection, might be like, based on word probabilities. This probability is based on a distribution that is separate from the topic distribution. And this process is going to be repeated 1,000 times because this book contains 1,000 words. I hope thus far I have clearly communicated the benefits of applying LDA to text analysis. Rather than having to read each document in our corpus individually, we can apply LDA to efficiently categorize which topic the documents belong to. However, it would be a mistake to think that LDA is a completely objective method, and this is because LDA requires subjective decisions from the researcher. In other words, LDA is able to provide replicable results, but it does not provide automated results. And this is because these subjective decisions might vary from researcher to researcher. These subjective decisions might be related to any of these 3 things. The first deals with the selection of hyperparameters, or variables that require initialization before the LDA algorithm can be applied in the first place. The first hyperparameter, J, deals with the number of topics. In our previous example of classifying books, we had 3 topics: romance, fantasy, and mystery. But another researcher, perhaps based on his or her domain knowledge, might decide that it is not 3, but 5 topics that are adequate to summarize the content of the 2 books. The second set of hyperparameters, alpha and beta, deals with the multinomial distributions where topic assignment and word probabilities are selected and drawn. Specifically, alpha and beta determines how concentrated or dispersed the topics are in each document, and how concentrated or dispersed words are for a particular topic. And these things influence how topics and words are drawn in the generative process that we have discussed previously. The second qualitative decision is with regards to naming the topics. The names for the topics are not generated by LDA and has to be selected by the researcher. In our previous example of classifying books, we had 3 topics of romance, fantasy, and mystery. But another researcher might look at the distribution of the words for these topics and label these topics differently. The third qualitative decision required from the researcher is cleaning the corpus. Rather than applying LDA to the raw data set, we might make the subjective decision to remove uninformative words, perhaps names of people, perhaps verbs, the decision to keep only nouns, etc. And so it is important for us as researchers to embrace LDA and topic modeling in general as both quantitative and a qualitative tool. And by applying these methods in our research, it will be beneficial for other researchers to clearly communicate any subjective decisions that were involved. LDA and topic models that extend the LDA algorithm have been applied very frequently in the past and is continued to be applied in extent marketing research. Simply searching topic model and marketing on Google Scholar returns more than 3.5 million results, supporting the popularity of topic models in marketing research. And so I only note a few examples of their applications. In 2014, Tiranoli and TELUS have used topic models to extract topics of product attributes from customer reviews. And they have used these topics to produce brand maps that inform marketing practitioners. In 2019, Netzer, Lemaire, and Hergenstein have used topic models to extract topics from peer-to-peer loan applications. After studying what consumers write about in their applications when they request for loans from their peers, they have used these topics to predict loan default. More recently, Wang, Ryoo, Campbell, and Inman have used topic models to study consumer research articles that were published in major marketing journals, and have used these topics to construct a measure of novelty to assess how novel a particular research article is to past research. To provide a richer illustration of applying topic models to empirical marketing research, I'll use my article as an example that I have co-authored with Shane Wang and CJ Liu, published in Journal of Marketing, titled Do Spoilers Really Spoil? Using Topic Modeling to Measure the Effect of Spoiler Reviews on Box Office Revenue. The main research question of this article is, what is the association between spoiler reviews and movie box office revenue? But the key points to focus on, as this article is being discussed in this video, is how can we measure the degree of spoiling in movie reviews? And how does topic modeling help us in identifying spoiling information compared to alternative methods? To provide some research motivation for this article, consider a very popular movie that was released way back, Avengers Endgame. When this movie was being marketed by Marvel Studios, there was a big campaign, #Don'tSpoilTheEndgame. This was an effort by the movie studio to discourage consumers that have already seen the movie to talk about sensitive plot-related information with their peers, because this had the risk of spoiling the movie experience for moviegoers that have not seen the movie yet. In this research, this is how we define spoilers: information that gives away plot-related content of the movie. What we find is that 1/3 of movie reviews that we have collected contain spoilers. As the majority of reviews are generated soon after the release of a movie, perhaps movie studios are right. Perhaps they should be concerned about the spread of spoilers amongst consumers. But this is conventional wisdom. Online word of mouth is beneficial for new products. Wouldn't it be the case for experiential products such as movies, regardless of spoiling information or not? And so this research deals with addressing this conventional wisdom. Is there truth to it? Should marketers be concerned about the spread of spoiling information? And if so, should marketers monitor spoiler reviews and adjust their marketing mix accordingly? To address our research questions, we collected our sample of movies from Box Office Mojo and IMDb.com. We constructed a panel data where I denotes movies and T denotes the days after the movie's release. We collected movies that were released in the United States from 2013 to 2017, and we were able to obtain 993 movies. We collected both online and offline advertising data from Kantar Media, and we focused on the first 8 weeks of daily box office revenue because prior research suggests that more than 90% of box office revenues are accrued within this time frame. For our sample of movies that were released in the United States, we collected their corresponding user reviews from IMDb.com, which is the most popular online movie review platform in the United States. We collected the conventional variables, such as valence or the star rating that the movie reviews gave, as well as volume for the movies, or the number of movie reviews that each movie received within the 8-week period after their release in the United States. Importantly, IMDb.com also has a policy where users that contribute movie reviews has to label their own reviews with a spoiler warning if they deem that the review contains sensitive plot-related information. For example, if you're writing a movie review on imdb.com and you judge that your review contains sensitive information, you must label your own review with a spoiler warning shown here in the example, or you would have your review deleted from the website and have your account blacklisted from contributing any further reviews on the website. So this provides us a labeled data set of spoiler reviews and non-spoiler reviews. And from imdb.com, we collected a total of 140,869 movie reviews. To provide some descriptive statistics of the data set, the average daily box office revenue for the movie is about $1 million, with a pretty large standard deviation, with $120 million for the most popular movie. We also find that for cumulative rating, the average movie receives about 6.27 out of 10, and that our sample is composed of a good mix of movies from various genres, with the most popular genres being drama, comedy, and adventure and sci-fi. Interestingly, we also find that about 40% of the movies are limited release, or movies that had less than 700 theaters that screened the movie on the first day of release. Again, the research question of this article is, what is the association between spoiler reviews and movie box office revenue? To address this research question, let us first consider a very simple regression model. As the dependent variable, we have the daily box office revenue for movie I on day T. In this regression model, we'll also include a lagged dependent variable as an independent variable to control for trends in daily box office revenue over time. As we have a panel data, we would also include fixed effect for the movie. This would control for time invariant heterogeneity of the movies. For example, genre of the movie, the cast of the movie, perhaps the intrinsic quality of a movie. Perhaps certain types of movies are more likely to receive spoiler reviews compared to other types of movies. These movie characteristics should not vary over time, and so should be captured by this movie fixed effect. We will also include control variables. Matrix X would include online word-of-mouth control variables, such as cumulative rating and volume, the star rating, and the number of movie reviews that movie I accrues. And Matrix Z would include marketing mix and time control variables. For example, advertising, the number of theaters that the movie I is screening on day T, as well as federal holidays and time trends that might impact daily box office revenue. This variable, spoiler, is a very simple measure of spoiler reviews. It is a binary variable that equals 1 if a spoiler review for movie I exists on day T, and equals 0 if no spoiler reviews exist. Or if movie review L belongs to the set of spoiler review for movie I on day T, and equals 0 if it does not. Again, we're able to construct this measure because the data set that we have collected from imdb.com clearly labels whether movie review L is a spoiler review or non-spoiler review. Let us examine the estimation results for our simple regression model. Foremost, examining the lagged dependent variable, or the box office revenue on the previous day for movie I, we find that the effect is positive and statistically significant. And this makes sense. If a movie garners a lot of ticket sales, the effect would likely carry over to the next day. Examining the other control variables, movies that receive higher user ratings and movies that receive a greater number of user reviews are likely associated with greater box office revenue. If a movie receives greater advertising expenditure from their movie studios, and if a movie has a larger number of theaters that screen the movie in the United States, these effects are likely positive on their box office revenue. Examining the time-related variables, we find that if a movie screens for a longer period of time in the United States, the time trend is negative, and that federal holidays have a positive impact on box office revenue. So the estimation results for the control variables are aligned with what we might expect a priori. Most importantly, examining the dummy variable that indicates whether a spoiler review exists for movie I is positive and statistically significant. And so from this, we might think that the effect of spoiler reviews on box office revenue is positive. Using the dummy variable of whether a spoiler review exists or not might be inadequate for our research. And this is because we must differentiate between two constructs, spoiler volume and spoiler intensity. Spoiler volume is countable on imdb.com. It measures how many spoiler reviews a movie receives. However, if we just consider spoiler volume, we're ignoring spoiler intensity. Consider a case that a movie garners a lot of spoiler reviews, but that these spoiler reviews each give away very little about the movie. On the other hand, a movie might receive a small number of spoiler reviews, but that these spoiler reviews give away a lot more of the movie. And this degree of spoiling related information in movie reviews is what we define as spoiler intensity. And this is a latent construct that must be measured using topic models. We believe that topic modeling is suitable for our research context to measure spoiler intensity because we believe that the topics that we extract from both spoiler reviews and non-spoiler reviews vary systematically. Consider this example here of two movie reviews for the movie Inception. On the top, we have a spoiler review as identifiable by the warning label, and a non-spoiler review on the bottom. By applying topic modeling, we can extract the set of topics that summarize both of these reviews. However, the topics that spoiler reviews discuss and non-spoiler reviews discuss should vary systematically. Spoiler reviews are more likely to focus on plot-related topics. In this example, relationship and death. Whereas non-spoiler reviews should focus on topics that are not related to the plot of the movie. And this is to avoid being tagged with the warning label. For example, the non-spoiler review might focus more on the topics of acting performance and cinematography, while focusing much less on the topics of relationship and death as compared to the spoiler review. In this research, we apply a specific type of topic modeling algorithm called a correlated topic model, or CTM. CTM is an extension of LDA. LDA generates the set of latent topics from a Dirichlet distribution. And because of this technical fact, the variance of the topics that are generated by LDA are independent of each other. What this implies is that the likelihood of observing one topic in a document is independent of observing other topics. But in the context of movie reviews, a more realistic assumption is that a person writing one topic is likely to focus on another related topic. For example, suppose we have two topics, the topic of character development and romance. If a person is writing a review and focuses on the topic of romance, it's probably the case that the person will also talk about the topic of character development. These two topics are likely positively correlated. And so CTM addresses this technical deficiency by using a multivariate Gaussian distribution rather than a Dirichlet distribution to model the topics. Examining the generative process of CTM, what we find is that the process is very similar to that of LDA, with the key difference being that the Dirichlet distributions in the generative process have been replaced by a multivariate Gaussian distribution with mean and variance. This technical extension from the generative process of LDA enables the variance of the topics that are being modeled to be correlated with each other. The number of topics that either LDA or CTM generates is a hyperparameter, which is again a subjective input from the researcher or a variable that requires direct initialization. This hyperparameter can be determined subjectively. For example, a researcher can randomly select a number of topics, examine the final topic quality, and then adjust the hyperparameter to re-estimate the topics. Or it can be done in a data-driven manner. And that is what we opted to do in this research. To select a number of topics, we used an algorithm proposed by Lee and Mimno in 2017, which is based on a geometric approach of word co-occurrences. What we find is that for our dataset of more than 140,000 spoiler and non-spoiler reviews, 61 is the optimal number of topics. But as good practice and for comprehensiveness, we also used other data-driven approaches proposed in the past. For example, minimizing perplexity or the surprise that the topic model faces during its estimation process. And what we find is that 61 is a good enough number when considering both of these data-driven approaches. But what is important to consider in this graph here that illustrates the perplexity between CTM and LDA is that CTM outperforms LDA consistently. What this suggests is that the correlation between topics is assisting the estimation of the topic model, and that the correlation between topics is informative in our setting of movie reviews. The names for the topics is another subjective decision from the researcher. Both LDA and CTM do not generate the topic names. These are things that the researcher must provide. To do this, we take the most representative words for each topic. For example, the first topic, the most likely or the probable word are perform, actor, role, cast, and so on. And based on these likely words, we label this topic as acting performance. And for the 61 topics that we have estimated, we use this process to name each of the topics that we have generated. Consider that we have applied correlated topic model to our aggregate dataset of movie reviews. Our dataset of movie reviews contain both spoiler reviews and non-spoiler reviews. In other words, the 61 topics that we have estimated, that we have generated using CTM, summarizes both spoiler reviews and non-spoiler reviews. But amongst these 61 topics, some topics may be more related to spoiler reviews than others. And so to identify these spoiler-related topics, we conducted logistic regression, where the dependent variable is a binary variable of whether review L is a spoiler review or a non-spoiler review. As the independent variables, we use the 61 topics that we have estimated and movie-specific dummies to control for movie heterogeneity. Now, as the 61 topics, the mixtures sum to 100%, we convert the percentage into word by multiplying the number of words for a particular review with the topic weightings. We conduct our logistic regression to predict whether a review is a spoiler review or non-spoiler review using the topics, and we isolate the topics that are statistically significant and have a positive coefficient. And these are the topics that predict whether a review is a spoiler review. We find that of the 61 topics, 23 are positive and statistically significant. And we can use the size of the coefficients to measure the importance of specific spoiler-related topics. To provide evidence of face validity behind our topic modeling procedure, we identify the topics that are most related to spoiler reviews. So these are topics that have the greatest coefficients in our logistic regression model. And also identify as comparison topics that are most related to non-spoiler reviews. So these are topics that had the negative and smallest coefficients in our logistic regression model. For spoiler reviews, we find that the three topics are disappointment, kill, and death. Whereas for non-spoiler reviews, the three topics are cinematography, expectation, and acting performance. And these topics appear to make sense. Spoiler reviews deal with the most sensitive plot-related information of killing and of death of characters in the movie, whereas the topic of disappointment appears to be correlated with spoiler reviews. If you're writing a spoiler review, you're most likely to be disappointed about the movie, and you're more likely to be writing a spoiler review to warn other potential moviegoers. For non-spoiler reviews, these topics are not plot-related. These are topics that can be elaborated on without touching too much on the plot of the movie. To construct our measure of spoiler intensity, we use word count associated with each of the topics that are related to spoiler reviews. Consider a non-spoiler review at the top and a spoiler review on the bottom. Because we have applied topic modeling, we can identify the specific words that are related to each of the topics. We focus specifically on the spoiler-related topics as identified using our logistic regression model. In this example, the topics of relationship and death. For these topics, we find that in the spoiler review, 28 words are associated with the topic of relationship, and 15 words are associated with the topic of death. And so, in total, 43 words are spoiling for the potential moviegoer. When constructing our measure of spoiler intensity, perhaps it is inadequate to simply take the aggregate sum of all the words that are associated with the spoiler-related topics. And this is because we must consider the real-life phenomenon of spoiling. And I illustrate this using this example. Consider two spoiler reviews, spoiler review A and spoiler review B for the same movie about time. Now, these two spoiler reviews touch on the topic of relationship, which is a very sensitive plot-related topic for the movie. When reading these two spoiler reviews, we take away different degrees of information for the topic of relationship. When reading spoiler review B, what we take away is that this topic of relationship in the movie is not run-of-the-mill, and that this movie takes characters and the relationships between their characters very seriously. When we read spoiler review A, we take away much more information about the topic of relationship. When reading spoiler review A, what we take away is that the main character, Tim, has inherited time-traveling ability from his father, that the main character, Tim, has a very close relationship with the father, and that the movie has an emotional ending, and that this ending involves the father. And so reading these two spoiler reviews, we take away varying amounts of information, even though they spoil the same topic of relationship. When I read spoiler review A, I am more spoiled about the topic of relationship for the movie when compared to reading spoiler review B. Consider if I read spoiler review A first and then read spoiler review B. I am spoiled of the movie when I read spoiler review A, but I am not spoiled any further when I read spoiler review B because spoiler review B doesn't give away much more information when compared to spoiler review A. taking the reverse order. When I read spoiler review B and then spoiler review A, the state of spoiling is influenced more by spoiler review A than spoiler review B. And so to take this into account, what we do is to take the maximum number of words that are spoiling for each spoiler-related topic. How this operationalizes is to take the number of words that are spoiling for each topic. So in this example, 37 words are spoiling for the topic of relationship in spoiler review A, and 19 words are spoiling for the topic of relationship in spoiler review B. And so when taking the sum, rather than summing both spoiler review A and spoiler review B, we will take the maximum. So only considering 37 words as spoiling for the movie About Time, at least for the topic of relationship. And so we can formally specify our measure of spoiler intensity as follows. We have identified 23 out of the 61 topics that are spoiler related. And so for our measure, we'll be focusing on those 23 topics. For each of those 23 topics, the topics denoted with J, we'll be taking the maximum number of words that are spoiling, those maximum number of words spoiling contained by some review L that belongs to the set of spoiler reviews for movie I on day T. But hold up, what is this alpha here that is denoted as normalized topic contributions? Consider that the topics that we have estimated using correlated topic model summarize the movie reviews that belong to all movies in our sample. Let's take this specific example of a spoiler-related topic of relationship. This topic of relationship belongs to the spoiler review of the movie About Time, which is a dramatic romantic movie. And also it's contained in the spoiler review for the movie The Lego Batman Movie, which is a more family-friendly movie. The spoiler-related topic exists in both of these spoiler reviews, but their importance in terms of spoiling are different. When we read the spoiler review for the movie About Time, again, deals with the sensitive topic about the main character Tim and his father, it gives away a lot of information about the movie. Let's compare this to the spoiler review for the Lego Batman Movie. When we read the spoiler review, what we find is that it deals with an information related to Batman and the Joker, but it is not very sensitive at all relative to the movie About Time. The contribution of this topic to spoiling for these respective movies are different. And this is what we attempt to capture using alpha. So exactly how do we calculate alpha, or a topic's contribution to spoiling? We base this on the logistic regression formula. Suppose that we want to predict whether a review L is a spoiler review or a non-spoiler review using our spoiler-related topics and movie-specific dummy variables. And that logistic regression formula would look something like this. To calculate a topic's contribution to spoiling, we borrow from the calculation of derivatives. What I mean by this is that to calculate the importance of a particular topic in increasing the likelihood of a review being predicted as a spoiler review, we assume that one additional word has been written for that particular topic J. And by subtracting it using the original logistic regression, we can then obtain the contribution of topic J, the additional word being written for that topic, and increasing the likelihood of review L being predicted as a spoiler review. By normalizing these contributions for each movie to vary across movies and by topics, we can then obtain our alphas that serve as a weighting in our measure of spoiler intensity. So, we have applied correlated topic model to our movie review dataset, containing both spoiler reviews and non-spoiler reviews. We have identified the spoiler-related topics contained in the spoiler reviews. And using these topics, we have specified a measure of spoiler intensity. Now, to ensure that our measure using topic modeling is representative of spoiling in real life, we validated our measure using human coders. Specifically, we recruited human subjects, presented them with spoiler reviews for the same movie, varied the spoiler intensity, and asked the human subjects to identify the spoiler review that was the most spoiling of the movie. And what we found was that spoiler intensity, what we constructed, was in agreement with human judgment. In fact, we found an overall agreement rate of 82.5%. Previously, we have discussed the importance of considering two constructs in the context of spoiling. Spoiler volume, or the number of spoiler reviews that a movie I garners, and spoiler intensity, or the degree of plot-related information that the spoiler reviews are giving away for the movie. So we can toss out the simple regression model that we have considered previously, replace the dummy variable that equaled 1 if movie I garnered the spoiler review and equals 0 if it did not, with our two measures. The intensity measure that we have specified using topic modeling, and this proportion measure that measures the number of spoiler reviews over the total number of views that movie I garners. And we keep the rest of the specification the same. We can now estimate our model results. Column 1 shows preliminary results with one set of instruments for the lag-dependent variable, whereas column 2 shows the results for the complete set of instruments for the lag-dependent variable, word-of-mouth related variables including the spoiler-related variables, and the marketing mix variables. What we find is that the effect of spoiler intensity on box office revenue is consistently positive and statistically significant. However, our measure of spoiler volume becomes statistically insignificant when we include all of our instruments. Taking this together, what we can take away is that it's not the number of spoiler reviews that matter, but how much information these spoiler reviews give away that's associated positively with daily box office revenue. I hope that you find these results interesting. The conventional wisdom in the movie industry is that spoiling information is harmful to box office revenue. But using topic modeling and our sample of movie reviews, what we find is that spoiler reviews have a positive effect. A 25% increase in spoiler intensity is associated with a 2% increase in daily box office revenue. To explore the potential mechanism of why we have just found a positive association between spoiler reviews, specifically spoiler intensity, and daily box office revenues, we examined differences of movies in our sample. The first difference that we examined was movies that had a wide theatrical release and movies that had a limited theatrical release in the United States. Again, this is dependent on the number of theaters on opening day. Movies that had more than 700 theaters on opening day is defined as a wide theatrical release. Movies that had less than 700 theaters on its opening day is defined as a limited theatrical release. And as we can see, movies that have a wide theatrical release are oftentimes movies of a higher budget compared to movies of limited theatrical release, which is often employed by movies of smaller studios or independent filmmakers. What we find is that the positive effect of spoiler intensity is much bigger for limited theatrical release than wide theatrical release movies. Specifically, a 25% increase in spoiler intensity for a limited theatrical release movie increases daily box office revenue by 7%. And this is in comparison to 1% for wide theatrical release movies. And so we argue that uncertainty reduction is what's driving the positive effect of spoiler reviews. To empirically examine the behavioral mechanism of uncertainty reduction further, we used user ratings as another moderator. We use user ratings as a proxy of movie quality. Suppose that we can organize movies based on their quality as follows. On the one end of the spectrum, you have high quality movies, such as The Joker, that gets 8.8 out of 10 on imdb.com. On the other end of the spectrum, you have low quality movies, a movie like The Emoji Movie, that gets 4 out of 10 on imdb.com. What we find in our data is that the positive effect of spoiler reviews are the smallest for these two types of movies. What about movies that fall in the middle? A movie like Zombieland and a movie like Terminator. What we find is that the positive effect is the greatest for these two types of movies that gets moderate ratings. Well, how can we interpret this in light of uncertainty reduction? Well, suppose that you're selecting a movie to see in theaters with your significant other. Reading spoiler reviews is not going to help you convince yourself to watch the Emoji Movie in theaters, because you are certain that this movie will be a bad movie. Conversely, you do not need spoiler reviews to convince yourself that The Joker is going to be a good movie. In fact, spoiler reviews are not necessary for you to select the movie The Joker in theaters. But what if your significant other has already seen the movie The Joker? Well, The Joker comes off the list and you must select between Zombieland and Terminator. Well, because of their moderate ratings, you are more likely to experience greater uncertainty in selecting which movie to watch. And it's this scenario where we argue that the positive effect of spoiler reviews come into play. You are more likely to read spoiler reviews to determine which of these movies that garner moderate ratings to see in theaters. So, what are the managerial takeaways from this research? First and foremost, we recommend movie studios and theaters to monitor spoiler reviews to forecast box office revenue. And it is not just summary statistics, as the number of reviews or star ratings, but it's the content that matters, or the intensity of the spoiler reviews. And we hope that this research provides a benchmark or a framework to construct a spoiler intensity measure using topic models. Second, we recommend online review platforms such as imdb.com and Rotten Tomatoes to not prevent spoiler reviews from being written, but to increase their accessibility. What does this mean? Well, we recommend these movie review platforms to not hide spoiler reviews, but make them accessible to those that want to read those reviews. Second, we highlight the importance of spoiler labels. Perhaps there is a group of consumers that want to avoid spoiler reviews in general because they want to preserve the enjoyment of the movie. As our research deals with box office revenue, not movie enjoyment, we highlight the importance of warning labels to increase the accessibility of spoiling information to consumers that seek such information in the first place. And these are likely consumers that experience greater uncertainty about the movie. Moreover, we argue that the positive effect of spoiler reviews are dependent on several marketing factors. For example, it is movies with less advertising, not greater advertising, and movies in the earlier periods after their release, not in their later periods, that experience greater positive effect of spoiler intensity. And this is consistent with the uncertainty reduction mechanism. Movies with less advertising, movies in their earlier periods after release, as well as movies that have a limited theatrical release and movies with a mixed user ratings on imdb.com, are the movies that instill greater uncertainty in potential moviegoers. And spoiler reviews provide a source of information for these consumers to decrease their movie uncertainty. And so we come to the end. I hope that discussing this research on spoilers have illustrated an application of topic models to empirical marketing research. And stepping back, I hope that this video was useful to you in providing an overview of topic models and the impact that topic models had on marketing. Thank you for your time.